variable a, which is going to be the angle from 0 to 90 degrees with a small step. Actually, the 0 to 90 degrees represents the half vector angle to the normal, which means that at angle of 90 degrees, we are actually calculating the angle of the view at 180 degrees, but we're actually looping through the possible half vector angles. Since at 180 we're going to get a half vector which is at 90 degrees, and whenever the two are parallel, then we get an angle of 0. Instead of calculating a dot product, we are actually taking just the cosine of the angle, which has the same result as the dot product of the two vectors, and then we calculate the x coordinate of the left and the right points that we're going to paint in the bitmap. Then we loop from the x1 to the x2 location and collect as many white colors in an array as the number of pixels between the 2 points. And finally we set this new white horizontal line starting at the left point x1, and at the level the y-axis is going to be the dot product that we calculated to the power of the glossiness value multiplied by the specular level. Now obviously the dot product can change between 0 and 1, and any value to the power of positive integer is going to return a value below 1 or maximum 1 if it's a fraction of 1. This means that our curve in this part of the equation is going to always deliver numbers between 0 and 1. And the specular level then multiplies this value in order to give it the strength, the level, the height that we want to achieve. We are also multiplying it by 0.5, but this is just a scaling for the bitmap representation. If we wouldn't scale, then a specular level of 100 would draw 100 pixels up, and we, in this case, is going to use only 50 pixels. Then we use the pixels that we collected in order to set the colors of the pixels from x1 to x2 inside the bitmap, and then we display the bitmap. Let's take a look at the result. If we evaluate the script, we get a curve for specular level 100 and glossiness 10. If we would change the glossiness to 1, we get the typical curve, and if we set it to 50, we get in a more sharp spotlight. At 100, we get it's getting even sharper, and so on. We can increase the specular level or reduce it and play with the values and getting very similar results to the ones that we're getting in the material editor when changing those values. Now that we know that our implementation of the Blinn specular highlight model is doing what we expect it to do, we can go back to our renderer and implement this model in a function there. Now let's add a function to calculate the specular highlight according to the Blinn model. Our function is going to be called getSpecularHighlight. And it's going to accept a couple of parameters. The first one will be the specular level. The second one will be the glossiness. Then the surface normal at the point of intersection, the light vector in the same point, and the view vector that led to the intersection. First we'll calculate the half vector by taking the light and the view vectors, adding the one to the other, and then dividing by 2. And the result is a new vector which will be normalized.